Okay, welcome everyone to my continuation of what are my favorite theorems. My very biased collection, of course, as usual. Today I would like to tell you about a theorem which I find like super counterintuitive. It's true and it's kind of a fun result, but it's like really, really counterintuitive in some sense. It's about the counting of abelian groups. Yeah, so if you count groups, I will kind of recall in a second what groups are, then this is like a really difficult problem. It's like terribly difficult. There are trillions of groups. There's no really any good way to count them. But if you count then the commutative ones, so commutative and abelian are the same. So really just whenever you have AB equals BA, that's abelian, named after Niels Hendrik Abel, I guess. Anyway, you can just substitute it with commutative. As soon as you add this condition of commutativity, somehow something magical happens and everything just gets super easy. And not just super easy, but also the numbers drop down so drastically that I really was shocked actually. The result is ridiculous, I promise you. The result of the theorem itself is like completely counterintuitive. In particular, if you're just learning about groups, most small groups you actually meet are abelian. Whatever you could think about something like a Z mod 7 or something. They're all abelian. Z mod 7 is just a placeholder here, of course. You can have something different. They're all abelian. And yeah, for a long time, if you study groups, maybe the only abelian group you usually see is the symmetric group. Symmetric group Sn, often denoted by Sn or some symbol that looks similar to an S. And then n is the number of, the size of the set you want to permute. And for a long time, this is like the only really non-abelian group that you see, and you only see those abelian groups, commutative groups. So you somehow get the feeling that everything is somehow a commutative group, an abelian group. But what I'm going to show you is essentially the opposite. And not just the opposite, well, we'll see, but not just the opposite, but the number of abelian groups is just so ridiculously small. I was kind of shocked how small it actually is. And this is what this video is all about. Trying to count numbers. Counting is always great. Counting things is always fantastic. And there's a famous function which is called the GNU function. So GNU, group number function. That's what it is. So it is a sequence on an integer. On an encyclopedia of integer sequences, its first entry is the number of groups of order n, and this function just spits out that number, right? So it takes an input and it just spits out the number of groups of that order. And groups are really just symmetries of certain objects, if you want. So dihedral groups, for example, act on a whatever n-gun. So D is 3 usually. 3 is kind of a strange notation. Maybe D6. Depends a bit on the notation. Let's say this is D6. Acts on the 6 gun by rotation, and there's one extra operation which is reflection. So and operations in together form an algebraic structure called a group, and we can just really think of them as being symmetries with n operations. So really just some finite number of operations. Like the dihedral group here has 12 elements. So the size of D6 is, for example, 12. So for the symmetry groups of regular polygons, it's always twice the number of vertices of that polygon because you have the rotations, but then you can reflect, and the reflect just gives you the times 2. Anyway, so this GNU function is really just a number of different groups of size n. And here's my favorite plot of the GNU function. As n goes like here, and here's the number, or rather the log plot of the number, because the numbers grow up really, really fast, and it looks insane. It looks like a starry night or something. It's just what's going on here, right? Completely random, and we know next to nothing about this function actually. Just for all finite groups, just counting those, we know next to nothing about it. And seriously, I mean next to nothing. So if you're taking a first lecture on algebra, you probably learn essentially everything that is known about that function. Something like something really not so difficult to show that, so for example, if you have a prime, like prime number, then this is just one. There's just one group of prime order. Now, these are all the ones here in this table. This is where this funny line here is very, very low. Okay, fine. But we really don't know much more about it, and that's essentially it. And that's a bit disappointing. Okay, should we give up? Finite groups are kind of random. So maybe we should give up here. Keep this picture in mind. It's like a random mess essentially. Well, maybe let's look at the number of abelian groups. It's really just the same. I call it the whatever, the A GNU function, and there's a corresponding sequence in a well-known sequence on again in the online encyclopedia, and it's really just the same. I'm just commuting operations. And do the same, and I wonder what's going on in for this number. And if I do the same plot, it kind of gets much better in some sense. Just have a look at this plot again. Pretty random. Here you can somewhat clearly tell that there are kind of layers in this plot. And yeah, we'll see that in a second. You can actually describe the layers very explicitly. So the task is to give up on describing the GNU function itself, which is like hopeless, and just count the number of abelian groups of a given order. Doesn't sound so bad, or if you come from this perspective of that we tried the same for the GNU function, then it actually sounds really bad. So right now, well, this plot kind of indicates there might be some pattern we can explore, but it's a bit unclear how far we can push it. Turns out we can push it like really, really far, and the only thing you really need to know is the kind of the Chinese remainder theorem, which kind of proves everything for you. But it gives you a classification of those, but I will just show you how the count works. So you don't need to know the classification itself. I just show you how the count works. Essentially, the classification says that it's some form of a Z mod P and some cross products of that. So do some prime factorization, and then you can kind of read off what kind of abelian groups you have. And here comes the count. The count is pretty beautiful. So you take your number n, you decompose it into its prime factors. So p1 to the a1, pk to the ak, kind of really the prime factorization. And then the number is just, you completely ignore the primes, which is kind of fun. So you kind of completely ignore the primes. You only look at the powers of the primes. And you take the number of partitions of the powers and just multiply them all together. And that's it. So just the number of partitions of the exponents of the prime factorization. And the number of partitions, for example, the number of partitions of 4 should be 5, for example, because what can you do? You can partition 4. It's really just saying you can partition 4 in the following way. You can just write 4. You can write 3 plus 1. You can write 2 plus 2. You can write 2 plus 1 plus 1. So this is meant as a partition. It's an integer partition. Or just 1 plus 1 plus, oh god, now I'm running out of space, plus 1 plus 1. So there are 5 of them. And it's kind of, well, maybe not super easy to count, but it's kind of a nice result anyway. So partitions of 4, there are 5 of them. And then you just do it. For example, if you want to know the number of abelian groups of order 1,200, then you just prime factor it. 2 to the 4, 3 to the 1, 5 to the 2, and you just take P4 times P1 times P5. There are 5 partitions of 4. There's 1 partition of 1, just this one. There are 2 partitions of 2, namely this one and this one. So the total number is 5 times 1 times 2 is 10. And that's kind of an interesting result. I kind of like this. It's just really explicit and gives you a nice way to count the number of abelian groups. Like just really without knowing anything about it, just the formula to count the number of abelian groups. And I think that's pretty cool actually. Yeah, so I like it a lot. And yeah, but the main theorem is not this count, which really just follows from the fundamental theorem of abelian groups, the classification of abelian groups, but the following ridiculous consequence of it, which is like a completely surprising result if you keep in mind that as a student you usually only see abelian groups. So you get this feeling that everything out there is an abelian group, but it turns out essentially nothing out there is an abelian group. Because the average number of abelian groups of a given order is a finite number. And it turns out it's like roughly it's around 2.93. So the average number of abelian groups is finite, and it's 2.3, like really finite. So if you're looking for, you just don't want to do the calculation, you just want to know how many abelian groups are there of order very large number. Well, it's roughly 2.4 on average. Sorry, 2.3 on average. To be precise, for the ones who want to be picky, it is a product of the non-trivial of the non-poles of the integer values of the Riemann zeta function. Fine, who cares? But really, it's just you take the average in the terms of arithmetic mean, which just means you sum over all of them. You just take the sum over all of them up to a certain point and divide by n. And this number, this function actually is bounded, and it converges to roughly 2.3, which is kind of really surprising, because if you do the same plot for all groups, it turns out that there's no way that this converges to anything. And this number is ridiculously small. So the average number of finite abelian groups for any n, no matter how large it is, the average number is something like 2.3, which is a bit absurd. And again, if you're a lover of kind of more number theoretical things, it's actually a beautiful number theoretical result, because it's a product of a certain values of the Riemann zeta function. And I feel like this is a ridiculous result. It's just, as I said again, it's kind of mind blowing. As a student, you only see abelian groups ever, and well, it looks like they are everywhere, and there are many of them, but there are not many of them actually. There are very few of them. 2.3 on average. That's not a lot actually. Roughly what happens here is that if you just look at the exponents, and then take an operation, the number of partitions, which grows exponentially. So you go to the exponents, and then something that grows exponentially essentially should grow linearly. And if you do that, and then take the average of them, divide by the linear factor, you get a finite number. That's essentially what happens. But anyway, so I think this is a ridiculous result. It's just 2.3. It's just completely strange. And it turns out that I always have this picture in mind that mathematicians like to generalize, but very often they actually generalize without well, and it's kind of a little bit difficult to really get the point why they generalize things, because the overall count of new examples is actually pretty low. So we can generalize. A generalization of an abelian group is, for example, a semi-simple ring. Don't worry about the semi-simple too much. It's a large restriction, but it essentially says it's a matrix ring. A ring is really an abelian group plus a multiplication, and every abelian group has at least one multiplication structure, so it looks like it's a generalization, because you have this abelian group which has one canonical multiplication structure, and then there might be different crazy multiplication structures. But it turns out that there are not so many actually, because if you do the same result, it's kind of fun, you could kind of do the same count, it gets a bit more difficult. You still get this product over the Riemann zeta function. Maybe this was a bad choice of color. You'd still get this product over the Riemann zeta function, but the overall average is maybe 2.5 instead of 2.3. Yeah. So abelian groups are generalized by rings, let's say semi-simple rings, because you can kind of vary the multiplication you have on that ring. And it looks like this is a vast generalization, but it turns out it's not really. You still get, well, you have 2.3 on average, 2.5 on average compared to 2.3, which is again, by the way, a very beautiful result. Anyway, I hope you enjoyed this video, and I also hope to see you next time.